In this video, we're going to take a look at the sampling distribution of the mean. When working with sampling distributions for means, the first thing you'll want to learn is the Central Limit Theorem. The Central Limit Theorem, in essence, states that with repeated sampling of a population, we can expect the distribution of sample means to approach a normal distribution regardless of the shape of the original population distribution. In other words, if we begin with the general population and draw samples repeatedly, the mean for each sample that we draw, if we take all of those means and put them together, our distribution is going to appear to be normal. In other words, unimodal, symmetric, essentially a bell-shaped curve. This is a very powerful theorem, and what makes it interesting is that that sampling distribution of the means will have a normal distribution even if the population is not normal. The larger our data set of sample means, the more normal our sampling distribution model is going to appear to be. When working on example problems related to sampling distributions, there are a couple of things that you need to know. You need to know that the distribution of sample means appears to settle at the population mean, mu. You also need to know that the symbol for sample mean is given by x bar, and when you see the symbol mu, a Greek letter, it refers to the population mean. You also need to know that the standard deviation of the sample means is found by the formula standard deviation of x bar equals sigma over square root of n, where sigma represents the population mean. The population standard deviation. Navigating all of the symbols and statistics and their meanings can sometimes be a bit tricky, so let's reiterate. X bar represents our sample mean. Mu represents our population mean. S represents our sample standard deviation, while sigma represents our population standard deviation. Notice that we're using Greek letters to represent our population, and we're using Latin letters to represent our sample. Suppose we're given the following information. For a sample of size n equals 36, find the probability of a sample mean being less than 12.2 if mu, our population mean, equals 12, and sigma, our population standard deviation, equals 0.95. In order to solve this problem, we need to identify our population mean, which we have already done. We've said that our population mean is 12. We also need to find the standard deviation of sample means, which is usually referred to as the standard error. Again, that's found by the formula sigma of x bar. In other words, the standard deviation of our sample means is equal to sigma, our population mean, divided by the square root of n, our sample size. In our case, we're told that sigma is equal to 0.95. We're also given a sample size of 36. Now let's work it out. 0.95 divided by 6, which is the square root of 6, equals 0.158. This is our standard error. Now that we've identified our population mean and our standard error, we're ready to determine the probability of a sample mean being less than 12.2 if our population mean is 12 and our population standard deviation is 0.95. What we need to do is take our population mean and our standard error and plug that into a formula for z. So we'll say z is equal to x bar, our sample mean, minus x, or minus mu rather, our population mean, divided by the standard error. Plugging in our values, it's going to look like this. 12.2 minus 12 divided by 0.158. This gives me a z-score of approximately 1.27. In other words, 1.27 standard deviations above the mean. So C equals 1.27, and we're looking for the probability of a sample mean being less than this. In other words, what percentage of our graph falls below z equals 1.27. You can use either a z-table chart or you can use a graphing calculator. We'll use a graphing calculator. If you have a TI-83 or TI-84, you'll start by pressing the second key, then distribution, which is above the variables key. Then you'll select option 2 for normal CDF. From here, you'll enter in a lower bound. Now, a lower bound can be, since we're looking to the left, we can establish a lower bound. Really, -5 or below is sufficient. I usually use -100. So my lower bound would be -100. My upper bound, of course, is just my z-score. And when we enter that in, we get a probability of 0.8979. If we convert this decimal to a percent, we would say approximately 89.79% probability of our sample mean being less than 12.2. When working with the Central Limit Theorem, there are certain assumptions and conditions that we need to take into consideration. The first is independence. The sampled values must be independent of each other. Next is our sample size assumption. The sample size must be sufficiently large. Our randomization condition, which states that the data values must be sampled randomly. The 10% condition, which states that sample size n should be no more than 10% of the population. And finally, our large enough sample condition, which is a no one-size-fits-all rule. Instead, we should assess it within the context of our data. Let's take a look at one more example. Carbon monoxide, CO emissions, for a certain kind of car vary with a mean of mu equal to 4.2 gallons per mile, and standard deviation, sigma, equal to 1.1 gallon per mile. A company has 80 of these cars in its fleet. Estimate the probability that X bar is between 4.4 and 4.6 gallons per mile. Let's consider our assumptions and conditions. First, let's determine whether the samples are independent. We can say that they are because the emissions for one car are independent for the emissions of the next car. Even if they are the same type, brand, etc., each car is independent of the next. Next, let's look at our sample size assumption. We're going to assume that our sample size is large enough. Randomization. Were these cars sampled randomly? In this case, we're not given that information, but although they're not randomly assigned, we can assume that they come from a simple random sample. In other words, we'll assume that it's a random sample of all cars of this type, even though the sample itself is not specifically randomly selected. Our 10% condition is satisfied, as our sample size is no larger than 10% of the population. In other words, the company has 80 cars in its fleet. These cars represent 10% of all cars of their type. Less than 10%, rather. As you can see, when we're given a problem, we will always be given specific information about each of our assumptions and conditions. In some cases, we'll just have to generalize or assume certain characteristics about our population in order to proceed with working out the problem. The first thing that we need to do now that we've identified our assumptions and conditions and determined that they've been met is to identify our population mean mu and our standard error. Well, I see right here in the problem that mu is equal to 4.2. So that was easy enough. Our standard error, which is equal to sigma over the square root of n, is equal to 1.1 divided by the square root of our sample size, 80. This comes from the population standard deviation and sample size given in the problem. Working this out gives me an approximate standard error of 0.123. Now we need to determine the probability that our sample mean is between 4.4 and 4.6 gallons per mile. In order to do that, I need to find the z-score associated with 4.4 and the z-score associated with 4.6. Keeping in mind that z is equal to the sample mean minus the population mean divided by our standard error. Our z-score for 4.4 is as follows. You can calculate 4.4 or 4.2 first. It doesn't matter. We'll do 4.4. I'm sorry, 4.4 or 4.6. Okay, 4.4 minus 4.2 divided by 0.123 is approximately equal to 1.63 standard deviations above the mean. Our z-score for 4.6 is 4.6 minus 4.2 divided by 0.123, which yields a z-score of 3.25. Now we can use our graphing calculator to determine the probability that our sample mean x bar is between 4.4 and 4.6. Here we have the approximate point where z is equal to 1.63. That's associated with 4.4 gallons per mile. Here we have the approximate point, 3.25 standard deviations above the mean, where emissions are 4.6 gallons per mile. We are interested in finding the probability or percentage that represents the region in between those values. Using a graphing calculator, type in the command second, distribution, which is above the variables key, and then again we're looking at that option 2, which is normal CDF. From here, we'll establish our lower and upper bounds. Our lower bound will be 1.63. Our upper bound will be 3.25. Entering these values will yield a probability of 0.051, which we can convert to approximately 5.1%. So there are a few of the basics concerning the sampling distribution of a mean and the central limit theorem.